We have learned digital watermarking. It embeds information about the intellectual property designer into the IP as additional design constraints. The watermarked intellectual property will satisfy these additional constraints and therefore has certain properties that can be verified to prove IP's authorship. We now study digital fingerprinting. First, why do we need fingerprinting? We know that digital watermark can be used to prove IP's authorship. However, it cannot distinguish different users who are using the same IP. When you sell your IP to 10 different customers and you find someone else is also using your IP, can you find out from your 10 different customers who has misused the IP? The answer is no, unless you can find a way to identify each copy of the IP, or you have to make different copies of the same IP. Digital fingerprint is a protocol that can make each copy of the object unique and distinguishable. Here is some comparison between digital watermark and digital fingerprint. First, they are both invisible identifiers that are embedded in the design permanently for the purpose of intellectual property protection. Watermark remains the same for all copies of the IP, while fingerprint must be unique for each copy. In other words, fingerprint is equivalent to multiple copies of distinct watermarks. Any fingerprinting technique has to address the following two fundamental problems: how to generate IPs with different fingerprints effectively, and how to distribute these solutions to the users. We now elaborate challenges for digital fingerprinting. First, in the face of IP generation, the challenges are how to create multiple, or in many cases, a large amount of solutions. And second, how to maintain the high quality of these solutions to keep the value of these IPs. And third, how to minimize the time and the complexity to generate multiple solutions. Ideally, we want to keep it close to the time and effort at the same level of finding one single solution. In the second phase of IP distribution, there are also several challenges. Uniqueness means that different users must receive distinct fingerprinted IPs in order to provide high credibility about their identity. And robustness requires it to be very difficult for attackers to remove or change the fingerprints. Finally, the fingerprinted IPs should be very different from each other in order to prevent collusion. This second phase is similar to the scheme that distributes fingerprinted copies of multimedia data or other artifacts. There are plenty of such established schemes that we can use. Therefore, in the rest of this lecture, we will focus on the first phase, which is the solution generation protocols. This slide highlights two different fingerprinting techniques. The first one is called constraint addition, where we start from the original problem and then we consider a set of fingerprint constraints. Combining these two, we form an augmented problem. We use the problem solver to solve this augmented solution to obtain a seed solution. This seed solution meets the original problem constraints, which means it has a value as an IP. In addition, it also meets the fingerprinted constraints. We can design these fingerprinted constraints in a way such that we can generate multiple solutions from this seed solution. This is what we call the set of rules for solution generation, which is based on the fingerprinted constraints and also the problem. And from one solution, this set of rules will create multiple solutions for us. From this flowchart, we see that the problem solver will be used only once, which means the runtime to create multiple solutions by constraint addition will be similar or in some sense identical to the time complexity for finding this seed solution. However, how to design this fingerprinted constraints, and then how to create the rules for solution generation, this can be very, very challenging. The second technique is called iterative approach. In this approach, we start from the original problem, which might be watermarked to reflect the designer's signature. We solve the problem to find a seed solution. And then to generate fingerprinted copies, we take the user or the buyer's fingerprint and then combine with the original problem and the seed solution to first construct a sub-problem, which is a small portion of the original problem. And then we use the problem solver to solve this small problem to find a solution for the sub-problem. By combining this sub-solution, the sub-problem, and the seed solution for the original problem, we can form a new solution for the original problem. This will be put in the solution pool with this buyer's fingerprint. If we need more copies of the fingerprinted copies, we can repeat this process and potentially using this new solution as the seed solution to repeat this process. And from this flowchart, we see the problem solver will be used many, many times. More precisely, to generate each fingerprinted copy, we need to use this problem solver here once. However, notice that here we are solving a sub-problem, which potentially will be much less complex than the original problem. So hopefully the runtime overhead will not be as high as solving the original problem. Now let's see an example. We use the graph coloring problem as the example here. Remember, the question is how to give each node in the graph a color such that any two nodes which are connected by an edge will get different colors, and we want to minimize the number of colors. And here is the solution to this problem. And assume that we want to find a fingerprinted solution which will be different from this original solution. We can achieve this by connecting these nodes B and A. And then instead of solving the original problem, we can take a look of their locality. And then we can easily find, we can change the color of E from yellow to green and then form a new solution. And if we want more solutions, we can add more constraints as from our fingerprint. And as one can imagine, eventually the quality of the solution may be dropped. And this problem can be solved by the constraint manipulation method. In this example, we consider a smaller graph and a solution to this smaller graph. What we observe here is we see the node E can also be colored by yellow. And as a matter of fact, it can also be colored by red. But however, node A cannot be colored by red. And node A cannot be colored by yellow either. And what we have learned from here is a node's color can be changed or not to obtain another solution. It all depends on the colors its neighbor has got. But checking the colors of its neighbors takes time, and there is no guarantee that we can always find a new solution, like in the case of A. It would be very nice if we can create more solutions by changing the color of specific nodes without checking their neighbors or their adjacent nodes. And we can achieve this by the node duplication method. In this example, we duplicate node A by adding a new node A complement or A prime. And we connect A prime with A and all the neighbors of A, B and E in this case. Now we have this new graph, and we're going to cover this new graph, which we call the fingerprinted graph. And we can obtain a solution such like this. And in this solution, one thing which is for sure is A and A prime will get different colors because they are connected by an edge. And also, these two colors, which is green and the red, can be used to color A in the original graph, either one of them, either green or red. This is because both nodes are connected to the same set of neighbors. So what we see here is by duplicating node A, we can get two different solutions. If we duplicate K nodes, we can easily create 2 to the power k distinct solutions from one solution. Now let's see another example. Here is a graph and a coloring solution for this graph. We see here node B, C, and D, they form a triangle or a clique of size 3. So we need 3 colors to color these 3 nodes. None of them can get the same color because they are all connected. And we can also swap the colors of node C and D to form a new solution. However, none of C or D can get the color of B because they share the same neighbor E, which has the same color as B. So now if we connected 2 pair of nodes, B and E, and also D and G, and now this fingerprinted graph has a very special structure. We see the triangle BCD, now they share the same set of neighbors, A, E, and G, outside the triangle. So now if we color this new augmented graph or fingerprinted graph, we can find a solution scheme here. And with this solution, we can easily generate a lot of different solutions. So for example, starting from this original solution, we can replace or swap the color of C and D to find a new solution. Or we can change the color of B from yellow to brown, and then let C and D pick any of the remaining 2 colors to form 2 different solutions. And for the same reason, when we keep B as red, C and D can also take any of the 2 remaining colors to have 2 other solutions. In total, what we have here is we can build 3 factorial, which is 6 distinct solutions from solving the problem only once. So this shows that we can generate a lot of different fingerprinted solutions by solving the problem only once, and then without compromise the quality of the IP. The final examples are on how to utilize don't care conditions to generate fingerprinted copies. We first consider the observability don't cares in the following circuit, where X is the AND of A and B, Y is the OR of C and D, and output F is the AND of X and Y. In this case, we see that when Y is 0, signal X cannot be observed from output F. Therefore, we know that Y equal to 0, X equal to 0, Y equal to 0, X equal to 1. These are the observability don't cares. Now we modify this circuit by connecting signal Y into the AND gate. Therefore, signal X becomes the AND of A, B, and Y. And we know that when Y equal to 1, this is the same as A and B. And Y equal to 0, this becomes 0 regardless of the value of A and B. But however, when Y is 0, this X is observability don't care. So what we have here is these 2 circuits, they are functionally identical. And so we can do place and route based on this circuit with this additional connection. And then we decide whether we want to keep this connection or not to embed 1 bit of fingerprint. And when we can find n such structures in the circuit, we will be able to create 2 to the power n distinct copies of the same IP, good to embed any n-bit fingerprint. The next example is on the satisfiability don't care. In this circuit, X equal to A and B, Y equals to A prime and B prime. From the truth table, we see that X and Y cannot be 1 at the same time. Therefore, we have a satisfiability don't care condition, X equal to Y, X equal to Y, and equal to 1. We know that the OR gate and exclusive OR gate, they're different. For example, when both X and Y are 1, OR give you output 1, and the exclusive OR give you output 0. However, we know this condition X equal to 1, Y equal to 1 is a satisfiability don't care. Therefore, in that case, we are seeing this X, the OR of X and Y will be the same as the exclusive OR of X and Y. Or we can replace this circuit by this circuit, where the only difference is the OR gate or the exclusive OR gate. So if we can find n distinct satisfiability don't cares, we should be able to generate 2 to the power n distinct copies. To summarize digital watermarking and the digital fingerprint, we see that in this simple flow of traditional IP development without any protection, we can get an IP with the highest possible quality by synthesis tools based on the original design specification. But however, we will not be able to prove our authorship, or if there is IP piracy happens, we cannot trace where is the source of the IP piracy. The idea behind digital watermarking is to convert IP author's signature into additional design constraints and then add it into the original design spec and use the synthesis tools to solve for IP that satisfies both set of constraints. In this way, we can hide IP author's signature into the IP and then can retrieve this signature to prove the authorship. On the other side, fingerprint adds IP user's signature into IPs as well. It will enable us to distinguish who gets each copy of the IP and allow us to trace the use of IPs. Finally, it is important to mention that both digital watermarking and digital fingerprinting, they are deterrents of IP piracy. They do not prevent attackers from misusing the IPs. But they do make the attackers to think twice before doing anything illegally. In addition, law enforcement is the only way to get the lost revenue back should IP piracy happens. However, digital watermarking and digital fingerprint are strong evidence to facilitate law enforcement.